Yeah, I'm going to give a presentation, probably a long overdue presentation for getting started with simulations in STAR. I'm sort of was thinking about how I should present, what I should present, and decided that I should target this at new users in STAR who are interested in just getting started in analysis and primarily starting from a simulation standpoint. But I suspect that there is something even more experienced users can get out of this. So I'm going to formulate this around a few questions. Why do we do simulations in high energy and nuclear physics experiments? So what exactly are simulations, and how do we actually go about running them in STAR? And then there's the question of how do we really go about running them in STAR? And then I'll briefly talk about what's coming next, and then try to wrap this up with a nice little bow on top at the end. So first I'll say, how do you get in touch? If and when you run into problems, there are two emailing lists, StarSimu and StarEmbed. Please feel free to reach out to the simulation and embedding team through either of these lists. If you have a simulation problem, simulation is appropriate. Otherwise, if it's an embedding issue, contact the embedding team on the embedding list. Mattermost may be a better forum, however, for most inquiries. I think this is something that we underutilize in STAR. I know I certainly underutilize it. So please, if you have an issue, join in the chat. If you have a solution, please feel free, when someone posts a problem, say how you've solved it. The more information that gets out there, the better. So I am the simulation leader in STAR. Zhang Lei is the embedding leader. We meet as needed on Thursdays at 10 a.m. Eastern Standard Time, and the meetings are announced on the two lists noted above. So please join those lists and participate. So why do we do simulations? Well, the answer is it's complicated. STAR is a complicated detector. It's comprised of many subsystems with multiple diverse technologies for both the detector elements and the readout electronics. It's a device that provides large acceptance for tracking, calorimetry, particle identification. It brings a lot of capabilities to the table in doing the type of physics research that you are interested in. But it's also it's the time projection chamber has 200,000-ish readout channels. There's 20,000 channels of BTOF information, 5,000 calorimeter towers just in our mid-rapidity calorimeters, with an order of magnitude more if you're looking at the shower max detectors in those devices. So it's a really complicated device that needs some help in understanding it. The STAR operates at RIC, which is the most flexible particle collider in operation. I think that is a fair statement to make. It can collide everything from protons up to uranium atoms in symmetric and asymmetric collisions, from root S down to around 7 GeV per nucleon, all the way up to 200 GeV per nucleon. Can go to lower energies if you are doing the fixed target program here at STAR. In terms of proton-proton collisions, we even reach higher energies. Now, the 510 GeV top energy isn't anything compared to what the LHC can achieve, but we beat them on polarization. We have detailed control over the alignments of the spin direction of the two protons. So STAR operating at RIC brings access to a large number of physical observables. You saw talks on two of those today from an experimental and theoretical perspective. So we have a great deal of control over the initial collision state. This allows us rather deep insights into the structure of nuclei, the dynamics of the quark-gluon plasma, and several other physics topics. So simulations are complicated. Why is where's the complication coming in from? So the particles that are produced in this collision undergo many physical processes on their way to being detected at the star. There's hadronization at the interaction point. Particles which are unstable decay along the way, although they may encounter material before they get to the point where they would otherwise decay. Energy loss and multiple scattering occurs as particles pass through detector components. They can interact electromagnetically inside of the beam pipe, inside of things that they encounter before getting to the TPC, producing electromagnetic showers, providing more particles into the mix, but not the one you're interested in. Hadronic interactions may occur as well, lower probability in the material in front of the TPC, but they do happen. And so these effects have some complication to analysis. The particles which you are interested in might be lost due to physical processes. They may be contaminated due to backgrounds. The tracking may get steered off onto incorrect hits because of background tracks in the environment. There's multiple ways that the interaction with materials can change what we're seeing, and we need to account for that. And we need a computer model to sort this out. So another area of complication is that the detectors in STAR, they produce electrical impulses that are in rough proportion to the amount of energy deposited by particles passing through the sensitive elements. The electronics in each subsystem then take those signals and they transform them into the digital information that can be read out, persisted to disk, and then later have reconstruction algorithms applied. So first of all, not every detector element is 100% efficient. That's going to impact the ultimate efficiency of reconstructing things on the end. Some detector elements may simply be dead, and you have to account for that. All of the electronics in STAR, they have some level of noise that's just occurring all the time as things are being read out. That needs to be modeled. Detector gains may vary from pad row to pad row in the TPC, tower to tower in the calorimeters. Different threshold effects then may come into play about what gets detected and what gets zero suppressed. Finally, STAR operates in a very dense background environment, and something like the integration time of a detector is important. I think currently all of our detectors are fast detectors in STAR, except for one. Our main tracking detector, the time projection chamber, takes 40 microseconds to read out, which, given the collision arrival times of bunch crossings at STAR, means the out-of-time pileup tracks from two separate minimum bias collisions will be present in the TPC as it's being read out in 200 GeV gold running. If you're looking at proton-proton, the pileup issues get a little bit more challenging. 40 events, 40 minimum bias events are piled up in a 200 GeV proton-proton interaction. And 400 almost every single bunch crossing that exists in that 40 microsecond time window results in a minimum bias collision at a 510 GeV proton-proton environment. So there are a lot of background tracks that are present in the detector as it's being read out that you have to contend with. All right, so many measurements require the efficiencies for detecting signals and understanding of the background contributions. In fact, I would say almost all of them. You can construct things that have ratios where the efficiencies cancel out the first order, but when you really try to get to the edges of your acceptance, you really do need to have some more detailed understanding of your efficiencies. So physical interactions with the detector, complicated background environments, and imperfect detection all need to be modeled. And simulations are what provide that information. The stuff that we cannot measure directly in the experiment, we can extract that from simulations. So, whoa, this is supposed to have, yeah, my animation is not showing up here. So, again, so we've asked why do we do simulations. Now we can address how. So we need to model the proton-proton PA and AA collisions at RIC. So we start with the collision of the two protons. You have some event generator which models the dynamics, whether it be Pythia 8, Pythia 6, Haijing, Herwig, modeling the collision of the underlying partons, which then go out and fragment and hadronize and produce the final state particles that we observe in the detector. So we need to take those final state particles that have been created by these event generators, and we need three things. We need a geometric description of the star detector that says where all of the materials are, where all of the sensitive volumes are, and how we are going to and what we are going to record every time a track passes through one of these sensitive volumes. We need a particle propagation engine. The tracks need to be propagated through the magnetic field, propagated through the materials of the star detector. And then finally, a simulation of the physical processes has to occur in each of the material volumes. And finally, as we reach a sensitive volume, we need to be able to score the hits. For example, the amount of energy deposited as we are passing through one of the TPC pad rows, one of the calorimeter towers, one of the forward tracking detector chambers. And that is what we traditionally do in our simulations and our simulation framework. There is a third stage of processing that must occur to get to a fully simulated event, and that is digitization. How do we go from the energy deposits that have been recorded by GEONT? GEONT 3 is the simulation engine of choice in STAR, and I'll touch briefly on why we use 3 instead of 4 later. Digitization takes it models the response of the detector and the electronics to these energy depositions. It's a phase of simulation that treats the instrumental effects, noise in the electronics, crosstalk between different elements of the detector, and threshold effects, gains, etc. It converts the energy deposited in each detector element into the measured signal. For example, the charge deposited in the TPC gas volume, the time at which the charges then arrive at the TPC pad rows, and then that can be converted and reconstructed into the three-dimensional position of the track at a given point along the TPC, along that point, the track's trajectory. It also importantly converts the signal that has been simulated into the same format as the real data that has been acquired during the physics runs. And that allows us to use exactly the same reconstruction chain as we use in our real data. A brief interlude here on the history of simulations in STAR. So we have an application called StarSim. It dates back to the very earliest days of STAR. It's enabled world-class physics at this point, I could say, for almost 20 years. We've periodically upgraded this piece of Fortran code to match the physics capabilities of the application to the experimental reach of the experiment. We've embarked recently on an effort to upgrade, taking advantage of 64-bit simulations. I believe StarSim at 64-bit is running and available. And we've looked at providing JON4 which is a JON4 application to support the hadronic calorimeter in the forward direction. As I mentioned before, I would touch on why we maintain a JON3 simulation package. And the answer is the electromagnetic physics that's contained in JON3 is more than sufficient to manage the needs of the mid-rapidity physics program. We do not have hadronic calorimetry, and JON3 has one advantage over JON4. It is significantly faster. Okay, so we've discussed two of the questions, why we do simulations and what they are. Now let's touch on how to actually run them. And this is where again, it can get complicated. The simulation workflow itself is fairly straightforward. You run StarSim to produce a simulation output file. These are called FZD files. And then you run in a separate chain, in a separate process, the digitization and reconstruction chains. And this is through a piece of code called the BFC, the Big Full Chain. Now, there are two ways to run StarSim, and I think it's worth, because there are legacy versions floating around, it's worth looking at the old way. This is the StarSim application. It is a pure Fortran application. And then the new way, using the star generator macros, interfacing through STJOntMaker. So as I said, there are many legacy Kumacs floating around. So the StarSim application, you simply fire it up by typing in StarSim. You configure the geometry with what's called a det-p command. It basically sets, in the lingo of Fortran, it sets some cards. It tells the memory management system that the geometry will be, in this case, Y2016A. This is a geometry tagging scheme that we have in STAR, which I should cover in this talk. I will just mention that if you ever use a geometry tag, make sure it has a letter at the end. We do not necessarily support a Y2016 geometry. That's a rough cut. Y2016A is our full production geometry. The highest letter in the alphabet would be the most up-to-date version. You also set the field, I believe it is calibrated in kilogauss. You tell it to load in a support library and create the geometry on the next line, this call to starlib xgeometry.so. Could somebody comment whether you see the cursor when I'm moving it?
No.
No. Okay. All right. So that that helps. Let me spend 1 second here.
Now I do.
You do now. Okay. Good. All right. So that's. Thank you. So then you tell it to open an output file, and then you run an event generator. In this case, we throw one particle, which happens to be a muon between 0.1 and 10 GeV. -1 to 1 in pseudo rapidity. We trigger 10 events and then we exit. If you need help, there's a dedicated help system in StarSim, but this gives you a general idea of the flow of how you do things. The more modern way is to use root macros. The Star Generator framework, we created this in order to provide users the ability to run from within a root macro, to simplify the integration of event generators and enable new features such as external decay packages. If you look in this area, there's many example macros showing how to do things. There's Dalitz decay macros, filtered Monte Carlo productions. You can integrate LHA PDF if you need detailed, if you need to have a specific simulation with a specific underlying parton distribution function. And you can always sort of shoot individual particles through the kinematics event generator. Typically, what I would do is I would just copy one of these macros, for example, starsimhyging.c to the local area. I would actually rename that to be starsim.c because within each of these macros, there is a function called starsim, which you will be calling. And then you fire the macro up, the arguments to each macro changes. So be aware of that. You'll have to open it up and look at it. But this generates 10 Hyging events in the 2016A production geometry with a random number generator of 1,111. So if you then look in the directory, it should produce an FCD file. A more interesting example is, and this is something that you could follow along interactively if you wish, or when you get home, when you get to your hotel room tonight, you can fire up a connection and fire off some events. So I have a little GitHub repository set up. If you don't know how to run GitHub, how to work with Git, I invite you to look at the tutorials that are on YouTube. They are very useful. So you can copy this macro, which is provided in this directory, and run off 10 events with Pythia 8 in the 2019A geometry. When you are running simulations, there are, I think, some best practices. Give your macro a good name. Make sure that the starsim function follows whatever naming choice you make. Use Git and GitHub to keep track of your work, and any questions that you have, post it to Mattermost, and we will get problems sorted out. So this particular macro generates events with a vertex distribution of 0.1 centimeters. Sorry, add a vertex of x of 0.1, y of minus 0.1, and a Gaussian width of 0.1, 0.1, and 30 centimeters in the x, y, and z directions. It's also set up to bias the partonic PT in Pythia 8. It runs pp min bias, biasing things to have a 3 GeV on average partonic PT. This is something that is useful in order to increase your statistics at high transverse momentum, but it's also something that introduces biases, and you should use it with some care. As I said, and maybe I have the vertex distribution set up twice in here, this is set up with a vertex of 0, 0, 0. I guess on an earlier, up further in the code, there's another primary vertex set. So you should, of course, whatever values you choose, put them in once in your macro and derive it from data. So go in, analyze your data, see where the vertex is, and place it accordingly. All right, so once you've run simulations and got an FCD file, now the fun begins. You need to reconstruct those events, creating a micro DST at minimum, Pico DST is what most people are using for analysis these days. So digitization and reconstruction are run in a separate chain, and there's an example chain that is provided again in this directory. When you are doing your work on whatever data set you are looking at, the goal is to configure an analysis chain which reconstructs the data under exactly the same conditions that were applied to the real data production. So you will find on this web page links. Gene maintains Gene and the production team maintain a production page that tells us what all of the chain options are for each production data set. And the general approach when you are modifying one of these chains to run on simulation is you need to modify it to read data in from the FZD file rather than DAC. So you would swap in with FZN and disable a few other chain options as well, and then add in slow simulators for each subsystem. So this can be, again, a somewhat tricky proposition. So again, I encourage you, if and when you have questions, please feel free to pose them on Mattermost, and people will help you out. So if all goes well, we've now taken and generated events, created an FZD file. We have run those events through a reconstruction chain and produced a micro DST and or Pico DST files. So you can always fire up a root on the micro DST and certainly on the Pico DST as well. The micro DST is a T tree. You can look at it as such, although it has, if you load in the new DST library, there are certainly other capabilities that you have access to as well. The micro DST contains a fairly complete Monte Carlo event record. We do not store the hits that are on tracks, but we store all of the tracks which were created by the event generator and then subsequently created by Geant as particles undergo interactions and decays. So you have access to all of the primary generator tracks, plus any of the decay and interaction products as particles interacted within the tracking media of STAR. But we do not save the full list of particles that are created in dense materials, such as the calorimeters, such as, well, material in the magnets. We only save the track which initiated the shower. These tracks can then be accessed through ID truth. So all of our reconstructed objects, when TPC track reconstruction occurs, we have access to the Monte Carlo event information. So we calculate which Monte Carlo particle was the dominant contributor to the reconstructed track. And from that, we can save the ID truth and a measure of the quality of that track. What fraction of the energy accounted for in that track belongs to the dominant contributor. So that's a very useful thing to have available to you. You can determine what the Monte Carlo resolution is, for example, by comparing the thrown and reconstructed transverse momenta for tracks. Furthermore, you have the ability to take the Monte Carlo track and go back to its parent vertex. And from that, you can go back as far as you can reach in the history of the track and find out what happened in the interaction that you are studying. As I mentioned, we do not save the hits on a track in the micro DST. That would be rather prohibitive. We only save the number of hits in each, the number of Monte Carlo hits in each subsystem on the track. If you need access to the hits, we have the complete Monte Carlo event record available. And that is something, again, reach out to us. If that's important for your analysis, we will help you analyze it. So then the question is, once you have started your simulations, how do you scale things up? That's one question. Another question is this a good idea? So the way you scale things up is by running multiple jobs on multiple computers. We have what is called the Star Scheduler. It is a system for submitting hundreds, thousands of jobs out onto our Condor batch system. The user manual is linked here. Levy back in 2019 gave a very nice tutorial at the Star Collaboration meeting, and I invite you to take a look at his talk. Over here is an example of a simulation of hygiene events using actually using the old classic StarSim macros that I was talking about, the legacy Fortran codes. And it shows the basic structure of how to formulate one of these XML documents. You specify the list of shell commands that you want to execute to produce your data set, where the output log files are going to go, and where your final set of files that are produced need to end up. And also any files that you need to send to the remote compute resource with your job. So there's several items of best practice that you should consider when trying to scale up your workflows to produce large numbers of simulated events. Test your jobs locally at a reasonable scale before blasting the farm with jobs that all crash 12 hours after you submit them. Then when you are convinced that things are going to run and execute and you're happy, test your jobs, submit a moderate scale submission to the batch system. Again, you don't want to discover that all of your jobs are crashing 10 events in to the system because you forgot to add something to this sandbox file. You should crawl first, then you should walk, then you should run. The batch system is a fair share quota-based system. So if you generate a large number of jobs that in the end you can't use, you've used up your quota, and it's going to take you longer in the end to produce the events that you want. So the basic one final caution, I've told you to crawl, then walk, then run. Don't run with scissors. Don't do direct writing to shared network disk resources. That is frowned upon. Use the ability to copy files through the sandbox mechanism when you need to copy files into your job, and then use this output directive to copy your files back from the job when you are done. Okay, so with that said, how do we really do simulations in Star? The answer to this is embedding. So why would we want to go through all of this trouble to tell you how to run simulations when we're going to really, at the end, suggest that you run through the embedding team? The short answer to that is you'll want to be able to test out new ideas quickly. There, you can run things in simulation on a quick turnaround time frame. Embedding is when you really need to get that final publication quality precision for your data analysis. for presenting things at conferences and eventually writing papers. So embedding is a technique that has been developed for placing a simulated event into the realistic background environment at STAR that has been measured during actual data taking. Assuming that we've sampled our background events properly throughout the run, the detector noise, the collision environment, the run-to-run variations of all these things come along for free. So the simulated signals in each detector are merged channel by channel with the measured backgrounds. We run typically in two modes. We either embed single particle simulations into minimum bias triggered data, for example, in gold, when we're interested in single particle reconstruction efficiency, or we can embed fully simulated events into zero bias triggered data when the vertex reconstruction efficiencies really matter. Straight simulations sometimes are not enough. So again, I've talked about this background environment. So the TPC integration time of 40 microseconds means that there are multiple events piled up, multiple sets of tracks that don't belong in your collision of interest that you have to sort through. Back in 2014 to 2016, we had an additional tracking system called the Heavy Flavor Tracker, which had two components which were insensitive to pileup, and a second component and a third which was subject to pileup, but not in the same way that the TPC was. So when we compared tracks which were identified in the TPC to those tracks which matched up with hits in the Heavy Flavor Tracker, we would find this sharp rise of events where simulations told us we were actually expecting something like this. This is the effect of pileup right here. At low PT, you have contamination of these background tracks that are in the time projection chamber, and that's something that is critically important to sort through. We don't generally use pileup. We can, but we don't simulate pileup. We do this process of embedding so that we use the backgrounds that have been directly measured, because it accounts for all the things that we cannot or do not know how to account for in simulation. So a typical simulation workflow involves reading in files from the DAC, from data acquisition, reading in the events from GEONT, digitizing those events, and then merging those events with the events pixel by pixel, pad row by pad row, before handing them off to our standard reconstruction chain, TPC cluster finders, the HFT cluster finders, and then on to tracking. So this is again a more complicated simulation task, and most of our large-scale simulations and embedding jobs are therefore carried out within the embedding group. It's led by Zhang Lei. He interacts with the PAC and SNC management to prioritize the jobs, matching them up to the available compute resources to maximize our maximize the physics impact that we can make in preparation for conferences and in getting out papers as rapidly as possible. So these embedding jobs, they will be discussed and approved and eventually requested by the physics working groups that you are working in, and then carried out by embedding helpers working within the embedding team. And I encourage you, if you are interested in doing service work for the collaboration, and I think all of you should be, becoming an embedding helper is one way which you can contribute to the STAR experiment and satisfy your your service tasks for STAR. So finally, I'm not sure how much time I have left here, but I'm getting near the end. So JAONT 4 STAR is what is coming in next. As I mentioned previously, we have not prioritized getting a JAONT 4 up and running at mid-rapidity because JAONT 3 does a good job of simulating the electromagnetic physics that our detectors are principally sensitive to. But with the forward upgrade, we do have a new hadronic calorimeter. So we have designed an application which leverages our existing software stack. It's designed as a direct drop-in replacement for StarSim and for the ST JAONT maker into our big full chain. It is based on the virtual Monte Carlo framework. And at present, it requires that we move to Route 6 in order to integrate. And so that is an effort that has been ongoing for some time now. We will continue that effort and get this ready to support the forward physics program. One of the features that recent versions of the virtual Monte Carlo allow is that you can mix simulation engines, so we can maintain a JAONT 3 simulation in our mid-rapidity detectors while sending particles passing through the electromagnetic and hadronic calorimeters in the forward direction. Those can be handled by JAONT 4 specifically. So that's a very interesting capability that should help us moving forward. I believe I have covered everything on this slide. We will go on now to the summary. So as I said at the beginning, I wanted to address a few questions. Why do we do simulations? Because we have complicated physics analysis and we need to understand some things that we cannot directly access through measurement. What are simulations? They're essentially complex computer models that are designed to provide the information which is not directly accessible from the experimental data itself. We run them in STAR using, there are legacy macros sitting around, so if you encounter them, and somebody may say, this is how I did my analysis, feel free to take it and modify it to suit your needs. You at least have a place to start now. If you want to start from your own, or somebody hands you a root macro, again, you have a starting point at minimum to start running these simulations. Our large scale, when you need the statistics, when you need the precision, that's handled through the embedding mechanism, the embedding framework. Yeah. So discuss it within your physics working groups, talk about what you need in terms of simulations, and then that conversation can be had with the embedding team as to how best to provide the data you need to produce the results that you want. And finally, what's coming next? JAONT 4, which will require that STAR move to Route 6. That's coming as soon as we can get things integrated and working. So with that, do you have any questions?
Hello, thanks for the talk. I have a general question about the simulation at STAR. So to the best of your knowledge, how well we trust the simulations at STAR?
Well, that involves a detailed comparison between the data that you are looking at and the simulations. So I would point you to, for example, So, again, this is something that has to be looked at on a simulation, an analysis by analysis basis. I know that the 2016 the studies that we did with the heavy flavor tracker, we were able to match very well the ratio of tracks that had HFT hits to the total number of tracks detected by the TPC, to a very high degree of precision. Can't quite quantify it off the top of my head, but it's the simulations are very well tuned and in general very well trusted. That does vary data set by data set. It's always a matter of going back and looking at calibrations, looking at the data, looking at the simulation, comparing it to it, and circling back to improve things.
Okay. The follow-up question is how, say, if I'm using simulation, if my analysis is simulation dependent, then how can I verify how well the simulation it is for my analysis? Say, for example, I'm using EPD, then how can I verify how accurately the simulation get the EPD hit correctly?
Well, I mean, you would, what I would say is you would start with correlations to downstream detectors. Now with the forward detectors, you will have tracking, so you will have an additional means to test that the simulation matches up with what you were seeing in the detector.
For the forward region, like EPD is at very forward region, so a lot of we rely on the correction. We rely on simulation to correct for the rescattering. Then how do we? Is there a way that we can estimate how well the simulation for rescattering is before particle reach the forward detectors?
Rescattering. I would, off the top of my head, I don't know because I just haven't thought through the problem that you are looking at. Invite you to open a discussion on Mattermost, and we can take it from there.
Okay, thank you.
Also, this is a good point to mention that we have a juniors Mattermost, which maybe all of you are familiar with, but that's also a good place to ask questions. Maybe the ones that you don't feel comfortable asking other people. Okay, do we have other questions? Yeah.
I have very general questions. Do we have the simulation on the triggers?
So there exists simulation makers for the triggers. They do not have a maintainer that I am aware of. So the code exists. It may or may not work. It may or may not work for the data set that you are interested in. It would have to be looked at.
Okay, so there will be like a table or some checklist to see whether for some triggers in some runs of data set and they already have some or they need to be improved or investigated.
Yeah, I mean, one would have to look for the data set and the set of triggers that you're interested in, making sure that everything is implemented and working correctly.
Okay, thanks.
So let's say I want to generate PTI events on my own local computer, but I want to use the settings that STAR uses in the STAR sim. Where can I find the exact configurations that were used in that PTI generation?
So the short answer is we generally use the default. We generally use the default settings of Pythia. When a user requests a simulation or requests an embedding job, they may request specific settings, in which case it would be recorded in the simulation request page, which is something that I had it in my mind to put on this talk. So we have a simulation and embedding request page. You can search for it in Drupal. I will add a link to this on the version of the talk that is posted right after the meeting.
Okay, thank you.
Thanks for doing that, Jason.
Hey, Jason, this is Eating from Rice. Good talk. Thank you very much. But I have a question. So how do we think about relationship between the embedding, the embedding and the simulation we run on the RCF? So is the embedding is just a better version of the simulation data? So let me make it more specific. For example, I want to do some machine learning using the simulation. Do you think it will have a huge difference if I using the machine learning using the simulation data or using the embedding data?
Yes. So and you should be very, I would say you should be very careful with machine learning on either of these. So with simulations, the challenge is always that they are too perfect. So you have a perfect detector. All of the channels are live. You have all of the detector elements in exactly the place that you put them in the design of the experiment, but not exactly where they are in reality. There are misalignments that need to be accounted for. When it comes to embedding, as I discussed, we embed simulated events into our real measured background environment. I can estimate what the impact of pileup is, and I can add in additional simulated tracks and do things all from the standpoint of simulation. But I'm making assumptions about where those tracks are coming from. If there's some source of scattering upstream of our experiment and particles are coming down the beam tunnel and getting through the shielding into the experimental hall, and I don't have that in my simulation, that can be contributing energy into my detector that can be interpreted as tracks. And so the things that we don't know about are why we do the embedding. And if you're doing things from a machine learning point of view, I think you definitely want to start with simulations to make sure that you are able to understand what is going on, because it is a simpler environment. Make sure that the training that you do on a training data set and a separate test data set in pure simulations, make sure that everything makes sense, and then go to the embedding to train on embedding before you go to real data.
Okay, thank you very much.
Hi, Jason. This is Diptanil. So I have a question about, say, like extracting the quark or gluon that started a particular hard scattering, say. Is it possible to extract that information from either mu DSTs or pico DSTs?
Not direct. Yeah, not directly. So there is an additional file that you would need to access that peeks back into the event generator record itself. And I will also caution you that at least the last time that I looked into this, if you're trying to do this with Pythia, I don't think the authors really take kindly in the idea that you look all the way back to the partons that initiated the shower. But my information may be out of date, or I may be misremembering that.
Okay, thank you.
So as I said, there's a separate file. It's called the gen events file. It is created by the event generator framework. And if you look at one of those macros, there's a place where you declare the name of that file. And if you have any questions of how to access it and access that information, please feel free to ask.
Jason, I just wanted to make a quick comment. I think with Pythia, you can access the initiating quark gluon with not too much problem just by the line in the event record. I think that.
Yeah, I know it's technically feasible. I just recall at one point hearing the authors saying that you should have some care about how you interpret that.
Okay, that's fair.
Hi, this is Kumar. Sort of a novice question, but do doing these simulations allow any room for some sort of background noise model, or would we strictly have to wait for the embedding process to consider any sort of background? Like, I mean, is through the simulation, do we only get just a pure signal and not any sort of noise?
So yes, so the simulation themselves has it's pure signal. I have to make a distinction between let me try to make a distinction here between phases. So at digitization, there are electronics noise which can be simulated, and believe they are. I know for the calorimeters, you get pedestal offsets generated. For the TPC, I'm quite certain that detector noise is simulated if you provide if you provide a timestamp within the real timeline of data taking. In terms of pilot backgrounds, we have the capability to simulate and add in pileup. It is not difficult to do. It is, however, time consuming. So if you need to have pileup backgrounds at an early part of your analysis, then I suggest opening this discussion at the PWGs sooner rather than later, and becoming an embedding helper and starting to learn how to run those simulations on your own, and then approach it that way.
I see.
But again, if you want to run pileup simulations, pure simulations, again, send me a question and I can provide some additional details.
Yeah, hi. So I have just a couple of quick questions. So you mentioned the geometry tags. Where can we find those tags, and what sort of geometry they correspond to?
So the geometry tags are listed. If you look in the simulation pages on Drupal, you will be able to find them. They may even be up to date. They will be up to date a little bit later today, if they are not currently. The general rule is that you should, at a minimum, use, if you're looking at the 2022 data, use geometry tag 2022A. Lately, we have only been generating one simulation geometry, one production geometry tag per year. In the past, we've had more, but we're stable enough in most of our subsystems to have just a single tag recently.
Okay. And just also, so you mentioned in the that the truth information, like what particle created the track. So when you say track, do you mean just the particle in general, or a physical track? Because in the forward direction, like for 2017, we didn't really have tracks. So
yeah, when I use the word track, it's just a sloppy on my part. I should be using particle throughout this entire talk.
Okay, all right. So it should be particle. So the particle information is in the MuDST under ID truth.
Particle information is there in the MuDST. It is accessible via the ID truth, which is stored in the reconstructed objects.
Okay, all right. Thank you.
Hi, this is Waving. So thank you for the next talk. I have a similar question to the first question. That is, how well can you reproduce the detector geometry? Is it an exact reproduction?
I would again say that where this mattered most was in the HFT studies, where we had to apply the misalignments in order to reproduce this HFT matching ratio, the ratio of the number of tracks with HFT hits to the total number of TPC tracks. And there we were what we were able to demonstrate is that we were able to position, to misalign to get the simulated geometry to within the expected resolution of the devices themselves.
I mean, in terms of the geometry and position, is there some kind of alignment measurements of each detectors to identify the exact positions?
Yeah, I mean, we were able to apply the measured measured alignments to within the resolution of the devices.
Okay, thank you.
And I'll just, as an aside, without the HFT, it is significantly less critical to get the alignment with that level of precision.
Okay, thanks, Jason.